So I'm going to tell you today how we are using Julia to accelerate systems biomedicine. Might be a topic that's very specialized, but I tailored the talk for everyone, for a general audience. So not to get you lost in the talk, I'm going to first of all tell you what COBRA stands for. I mean, it's definitely an interesting name, and you might be curious what it really stands for. Then I'm going to show you how Julia is used in the COBRA community to actually tackle large and huge scale modeling. And then just to get you familiarized, what we're commonly doing is actually flux balance and flux variability analysis, so that's just to give you a brief background. And then I'm going to go and dive right into the heart of distributed FBA, which is actually part of cobra.jl. And then, of course, everyone is interested if we are using a new language, new implementation, how does it perform compared to other implementations? So I'm going to show you that. And then I'm going to show you briefly how to get started, and I'm going to conclude my talk with an outlook. So what is COBRA? Well, COBRA stands for Constraint-Based Reconstruction and Analysis. And basically, it's just a widely used approach that we use to model actually biochemical networks at a genome scale. So we are using COBRA methods essentially to performing analyses and to understand how biochemical networks and mechanisms really work. So it is a relatively new method, but it has rapidly developed over the last few years. So you can see here, I also posted it on the Slack chat to invite everyone to this talk. You can actually see a representation of a stoichiometric matrix. And that's actually a small model. It is 3,800 reactions and around 2,700 metabolites. And it's actually, as I mentioned, a small one, but it's probably the only one that we can represent in such a beautiful and artistic way. So this is actually a human model, a reduced size model of that. So our groups in Luxembourg, we are developing, as I said, biochemical networks. And you might think, well, if it's such a nice idea to represent a network, then feel free to browse to vmh.live. And it's actually a Google Maps API that's being used. And you can pan around in the map and select origin and endpoint, and you can actually browse around on the human map or the network and discover it graphically. So that's all cool, and it's all really nice as well to play around with it graphically in your browser at home. But it gets really, really complicated when these networks become really big. So just to get you some background information, you might be familiar with the concept of the stoichiometric matrix. So any general chemical or biochemical reaction is generally written as a product A of a quantity small a, and another product B of small quantity B that are actually acting together. They are called the reactants, and they give us generally more than one product. In this example, it would be C and D. Now, the small letters, the quantities, they are called the stoichiometric coefficients. And this reaction, be it in engineering, biochemistry, or biology, happens at a certain rate, reaction rate, small v. So essentially, when we put these products together, or reactants together for formula, A and B, basically we don't know how fast they are going to react. And just imagine that now in a bigger and larger network. So essentially, what we do is we are balancing the mass. So we are saying, you know, whatever gets produced or whatever gets input to the network also has an output. So by some development, you can actually find that you can rewrite that equation, the chemical equation, as a mathematical equation, which would be S times V, S being the stoichiometric matrix, equals to 0. And S, in this case, would be defined as a 4x1 matrix, so there are 4 metabolites, 2 would be consumed, 2 would be produced, so you would have minus A, minus B, and then C and D would be the quantities that will be produced. So that's all very easy. Now just imagine you have 10,000 reactions, or you have 100,000 reactions or more. So why exactly do we need COBRA? Well, essentially, we don't have yet enough information to actually model a biochemical system. So essentially, if you have that large of networks, such as a human body model, for instance, you don't necessarily know what you're looking for, so it's sort of like looking for the needle in the haystack. So what we are using Cobra for is really to guide the biological hypothesis development. So we're trying to explore the networks, and based on our explorations and analyses, we can then formulate a biological hypothesis. That might sound very abstract, but it's actually something that we're doing in Luxembourg, where we are looking for finding biomarkers or hints to why some diseases might have happened or happening. And one of them is actually Parkinson's disease. So we are leading center there in finding biomarkers and finding why the Parkinson sickness disease is actually triggered. So the Cobra predictions themselves, they are actually relying on optimization problems, and they can generally be formulated in a form of minimization of a certain convex function that's dependent on the flux of all of the chemical reactions under constraints. So you have some biological constraints that you cannot go faster than a certain limit, and obviously you have the mass balance in there, which is generally written as S times V is equal to B. So a common analysis that we're doing is flux balance analysis. So that just means that whatever is input to the network is output as well, so it's basically at the steady state. And so what that comes down to is we take the original problem that I just formulated, and we're putting psi of V as being a linear function of the flux vector V. And we're setting B is equal to 0, so there's nothing produced inside of the network. And we would get an LP, a linear program, very simple, minimizing or maximizing a certain reaction. So that certain reaction in the network, that can be the biomass production rate, for instance, where we're saying we're having an organism that is producing energy, and we're trying to maximize the energy that that organism produces. Now, when we're solving this mass balance problem, basically, or that LP, we're getting a unique objective, but there might be certain solution vectors or solution rates that might exist that yield the same objective. Now, this is all nice if you know C. But just imagine in like a large network of 100,000 reactions. What is C? Which reaction is the one that is prevailing? Which one is the one that you should be looking after? If you're having a human body model and you're looking for what is causing Parkinson's disease, what are you looking for? How do you define C? So that is all the challenge. And for that, there is a flux variability analysis where you can actually go and say, if C is generally not known, what if we try every C? Well, you know, if you're having 100,000 reactions or more in your biological network, optimizing that, minimizing and maximizing comes down to 2n linear optimization problems that you need to solve, which is really nice because it's an embarrassingly parallel problem. I mean, you can literally give all of the different problems to different threads on your machine, and off you go. I mean, you just run all of them. So it comes down to hardware. Now, this flux variability analysis is actually, we're choosing one of these C vectors, let's say we call it D, and we're actually most of the time constraining it as well to at least the minimum rate that the network has to grow, for instance, a minimum biomass. So you can also see here a stoichiometric matrix that's already a little bit bigger, and that's still nice. It's a very small organism, the E. coli model. And you can see that there is already one reaction, so reactions are actually on columns, like vertical columns. And then you can see that one is standing really out, which has quite high coefficients. So, and others, they are relatively low stoichiometric coefficients. And there you can already see the first problem happening, that the stoichiometric matrix is very sparse, but might have very high scales of different coefficients. Now, you might say, well, you know, 100 reactions is still very small, but how does it develop, and what is the future for this? And why do we need Julia, actually? Now I talked about all this Cobra. Well, if you're looking at the evolution over the past few years, we always had models that were, let's say, below 10,000 reactions. And it was actually feasible to solve these models in MATLAB. So people didn't even bother about parallelizing this, because it took maybe longer. If you had 10,000 or 12,000 reactions, it just took a while longer, but you let it run overnight and no one bothered. But the problem is that now more and more, these models that were originally developed, they get put together in a bigger model, because you can think of it as one cell that's being put together with another cell, and it will create an organ at some point, and then you put an organ together with another organ, and it will become a human body. So if you're putting all these reactions in one network, it becomes bigger and bigger and bigger. And actually, right now, we're already working on models that have 1 million reactions or 10 million reactions. But what is the future, 100 million? So we still need to perform flux variability analysis on these models. So that's where we said, okay, let's turn to Julia, and let's see how Julia can actually help us. So for small models, like, say, 1,000 reactions, which we call very small models, actually, kilo-scale models, that can actually be efficiently solved. So we are not focusing on really going and getting there any speed gain, because it's on the order of seconds or minutes even. So the gains wouldn't be that significant. So they can be solved today with the Cobra toolbox, for instance, or CobraPy, which is an implementation in Python of Cobra methods. But basically, when you're going for very large scale, you're hitting a temporal limiting factor. So I joined the LCSB about a year ago, and at that time, we performed FVA analyses on large models like the one that you see here, on the order of 15 to 20 days. Today, we can solve it a bit faster. So you can see here the stoichiometric matrix, for instance, that's a prototype human body stoichiometric matrix. And what you can see that there is S, the stoichiometric matrix itself, and then you can see plenty of coupling constraints. And generally, the coupling is the thing that really causes numerical difficulties as well, because they are on a very different order of magnitude. And so in this plot, the order of magnitude is actually proportional to the size of the dot in the SPI plot. So the Cobra.jl package, actually, it's a high-level package where we're really trying to just give high-performance methods to the community, the Cobra community, who is actually aiming at developing these very large-scale models. So Cobra.jl itself is actually a multinodal analysis package. So you can use multiple nodes, computing nodes, as well as multi-threads. So you can, it's really tailored for parallelism. And so Cobra.jl, yesterday, there was a speaker talking about the name is everything. So it's a registered package. And we're actually happy that we have Cobra.jl registered under the umbrella of officially released packages. So it's also a well-documented package and tested package as well. It's also multi-platform, so most of the biologists in our community are actually using Windows operating systems, but they can use Cobra.jl. To get you started, there are also some Jupyter notebooks that you can use to run your first flux balance or flux variability analysis. So Cobra.jl started about 8 months ago, so it's still a very small package. But essentially, there is one function that is the distributed FBA function I'm going to tell you. So how does that really work? Generally, people, biologists, they create a .mat file or a model that's stored in a .mat file that comes straight out of MATLAB. And they're using it essentially with the Cobra toolbox. So the idea was really to be compatible with that, to get one of these .mat files, to read it in, and then to output the minimum and maximum reaction rates that are required to perform the flux variability analysis. So here we're having a host where we're launching our analysis, and we're basically loading up our model, and then we are solving all of the different reactions, minimizing and maximizing. And the interesting part is here is that we really did not focus on getting a solver written, because there is the package jump, and among that is mathproc-base.jl. And I was throwing quite a bit to Miles as well to get the solver compatible with what we needed to do. So how do we solve then each and every reaction? So basically, it's all Julia. And what we're doing is we're spawning up n threads. And on each of these threads, we are trying to solve a certain number of reactions. So let's say on thread 0, you get the first reaction until another n reaction. And thread P, you go and you put another block of reactions. And for each of these reactions, you're running a minimization and a maximization. So I put a few lines of Julia code there, which is actually the core of the distributed FBA package. And what you can see is that it is really just these few lines that do the entire analysis. And that's beautiful, I think. And if you were to go in MPI, you would write hundreds of lines of code to get the parallelization working. And when I discovered the macro @spawn@, I couldn't believe it, because when you're actually working on MPI itself, you have to find whenever your worker is ready and whenever not. So the @spawn@ macro really guides to which worker you're giving the reaction. So obviously, when you're splitting up your reactions among all of the different workers, you're trying to do it as efficiently as possible. So there are several strategies that you can use to distribute them. So one of them is actually just blindly splitting them. Just give the first reaction to the first worker, the next reaction to the next worker, and so on. However, that might not prove the most efficient one. So we tried out to play a bit. Of course, you could do dynamic scheduling. But essentially what we did find, though, is that there are already some speed increases just by distributing the reactions among the workers. And one of them would be to give a very tough problem to one worker and a less so tough problem to solve to another worker. So the toughness of the LP problems that are being solved actually depending on the density of these columns, or in other words, the number of metabolites that participate in each reaction. So the fewer the metabolites there are, the easier it is to solve the linear program. Now, you were wondering probably about the performance and the benchmarking itself. So the first model, 3,800 reactions, very easy. But there are other models out there, let's say 210,000 reactions. And so there really, the performance can be found with Julia. So what we tried to do is actually to compare it to the commonly used fastFVA function. And what we found is actually on 32 threads, so this is on one node, we actually get a speedup factor of up to 2. So that has primarily to do with MATLAB guiding the different LPs, how they're being distributed and being reassembled. So Julia is definitely faster in that. So that was also good to confirm that parallelization works. But on very small number of threads, MATLAB is almost as efficient as Julia or the other way around. So, but it's not where the main performance gain is. So essentially, what I was looking into is how does that distributed FBA scale? When we're going for very large models, the multi-organ model here that you can see actually has around 70,000 reactions, so it wasn't that big, but we looked at how it really scales up. And so what you can find is actually on 256 threads, you're getting a speedup factor of 32. So you might say, well, you know, what does the theory say about that? Well, if you're looking at the Amdahl law, you can actually get a theoretical speedup. So based on how much parallelization can be done in your code, including the model, you're getting a speedup factor that's actually predetermined by the number of threads that you are using and by the parallelization factor. And what you can see here is that the Julia implementation actually follows very closely the Amdahl, the theoretical speedup. So in theory, we could not go faster, although there were some dots where we were faster than the theoretical predictions. So of course, when you're taking now a larger model, I couldn't, let's say, load up a model of 200,000 reactions onto 2 threads, so that's why I didn't plot it here. But actually, if you're loading up a very, very large model, 200,000 or more, or a million reactions even, and you would just scale it up to 512,024 threads. So I keep this very short, but it's however interesting to see how simple really that distributed FBA package is. So basically, you start by choosing your solver. There is any solver that you can choose from Mathblock Base, be it Cplex, Gurobi, GLPK, whatever it is. And you can actually set also the parameters. And these parameters, we're working on it to auto-tune that solver interface as well, depending on the different models. And so then you load in your model using the package mat.jl. So Cobra.jl is really a package where we're trying to reuse other packages as much as possible, which has an advantage, but also other disadvantages. Because if one package breaks, you need to keep up and chase people to get their package ready because we are depending on them. So an FBA analysis is at the end of the day just one line. Let's say we want to optimize the 13th reaction in the network, which in this case would have been the biomass, let's say, or you can also give the name of the reaction. And you can actually choose whether you only want to maximize, minimize, or both. And in one line, you can now just call that. So that's for one reaction. Now, if you're going for larger models, it's not much more difficult. You just give the number of workers, and in this case, we connected all of the workers through different nodes, so we were not yet on an HPC, but we were connecting to different computing nodes via SSH. You're creating your pool. That means you're starting up all of your workers remotely, which is, by the way, very impressive to see that on 10 different computers spinning up 500 Julia sessions. That's very interesting to see. And then you're using your Cobra package everywhere you want on each worker. And then you launch distributed FBA. And distributed FBA takes care of distributing your reactions to the various workers according to the strategy you choose. Now, you can also say, well, I'm only interested in that reaction or that reaction. I want to only minimize or maximize and so on. So you can actually give a certain reaction list with an optimization mode. And once you're done, you can actually save it, save the results, the flux vectors, and as well as the optimization values as a mat file, which then you can post-process in MATLAB, let's say. So, just to jump to a conclusion. Distributed FBA definitely matches the theoretical predictions of how to scale up, which is in itself already a pretty nice achievement to see how really Julia is not causing any big overhead when you're distributing that many reactions. So the resources there are pretty much optimally used because you don't get any overhead, really, minimal overhead, let's call it. It's open source, you can use it right away. Platform independent, that's a big point, as I mentioned before. And of course, for an environment that really has the custom to work on MATLAB, you don't have any licensing or thread limitations or node limitations. So basically, we can definitely perform now an analysis faster than we were a year ago. I mentioned before that we can definitely solve it much faster than 20 days or 15 days. We can do it today, 200,000 reactions in about 9 hours. So that is a huge achievement for the Cobra community to run a flux variability analysis on a human scale model within 9 hours, which still is very long, but we are limited here on Highway. So I was talking to some people from the Celesti project to get eventually bigger hardware. Definitely our analysis possibilities in the Cobra community are lifted to another level. So what is the future? Well, basically, we're having a nice project, Optis, and we're really trying to run now the distributed FBA on large and huge scale models with more than 1 million reactions. So, however, on the back end, we're also working on the development of new solvers, not necessarily relying on Cplex or Gurobi, especially for large and multi-scale models, and it's especially that multi-scale component that causes most of the trouble. Then we want to increase as well the package functionality itself. I mean, right now it's pretty much limited to flux variability and flux balance analysis, but it would be nice, instead of doing the reconstruction in MATLAB, to do the reconstruction as well within Julia. So we can talk maybe about that offline and later. Collaborations are really welcome. We are looking for collaborations to help us. And yeah, so I'm concluding here. There are some references, just put it up for people who are interested. And yeah, that concludes my talk. So thank you very much for your attention and assisting my talk. Thank you.